The geometry of acceleration. Velocity is blind to curvature. Acceleration reveals geometry. Close your eyes for a moment and imagine two people. The first is an astronaut, floating weightlessly inside the International Space Station. She's circling Earth at 17,500 miles per hour. The second is a passenger, sitting in an airplane on the runway, accelerating for takeoff at just 150 miles per hour. Here's the puzzle that should keep you awake at night. The astronaut, moving more than 100 times faster than the airplane passenger, feels absolutely nothing, complete weightlessness. She can float, tumble, play with her food in midair. Meanwhile, the passenger, barely crawling by comparison, is pressed back into their seat with what feels like crushing force. Their chest feels heavy, their arms feel like lead. Why? What's the difference? Speed clearly doesn't matter, so what does? Your physics teacher gave you an answer. They said, acceleration is the rate of change of velocity. It's written as A equals dv dt. Change in velocity divided by change in time. Put it in your calculator, get a number, move on to the next problem. But here's what nobody told you. That definition, while perfectly useful for passing your physics exam, is hiding something profound, something that connects phenomena that seem completely unrelated. The spiral of an electron in a particle accelerator, radiating light as it curves, the weightlessness of orbital motion, the mysterious oscillations in quantum mechanics that give rise to the wave-like behavior of particles. All of these are manifestations of a single geometric principle. And that principle is this: acceleration is not fundamentally about time. It's about geometry. It's about curvature. It's about the shape of space itself. Today, we're going to explore a revolutionary paper that proves this claim rigorously. We'll discover what acceleration really is, why the classical definition misleads us, and how understanding this truth unifies all of physics under one elegant geometric framework. Let me start with what they taught you in school. Newton gave us this definition. Acceleration is the second derivative of position with respect to time. Mathematically, it's written as A equals d squared x divided by dt squared. Take your position function, differentiate it once to get velocity, differentiate it again to get acceleration. This works brilliantly for solving homework problems. Launch a projectile, calculate its trajectory, predict where it lands. But it has a fatal flaw that reveals it's not the fundamental truth. The flaw is this: it depends on your coordinate system. Imagine you're describing the motion of a car going around a circular track. If you use Cartesian coordinates, x and y, you get one set of numbers for acceleration. If you switch to polar coordinates, r and theta, you get completely different numbers. Same car, same motion, but the formula gives you different results depending on how you choose to measure. This should bother you, because acceleration is something you feel. It's real. It's physical. When you're pressed into your seat on that airplane, that sensation doesn't depend on whether someone watching you is using Cartesian or polar coordinates. The feeling is the same regardless of arbitrary mathematical choices. The classical definition is what we call coordinate dependent. It's not an invariant. It's not intrinsic to the motion itself. It's a projection, a shadow of something deeper. To find the real definition, we need to look beyond the shadow. And this brings us to the key insight from the paper. The standard view says acceleration is a temporal derivative, something about how things change over time. But the paper proves something different. Acceleration is a geometric invariant. It's the measure of deviation from geodesic flow in curved spaces. It's coordinate independent, observer independent, and fundamentally about the shape of the space you're moving through. To understand this, we need to talk about curvature. And I'm going to show you curvature not through abstract equations, but through a simple thought experiment, a paradox that reveals everything. Imagine you're standing at a street corner in a perfectly flat city with a perfect grid of streets. You want to reach the opposite corner of the block. You have two options.
Option A, walk east 3 blocks, then turn and walk north 3 blocks. Option B, walk north 3 blocks, then turn and walk east 3 blocks. Simple question. Does the order matter? Do you end up at the same corner either way? Of course you do. East then north gets you to the exact same corner as north then east. In flat, Euclidean space, the order of operations doesn't matter. North and east commute with each other. Now let's change the geometry. Imagine you're standing at the North Pole of Earth. You want to visit 2 points on the equator, one at 0 degrees longitude, the prime meridian, and one at 90 degrees east, a quarter of the way around the planet. Path A walks south from the North Pole to the equator. You're now at 0 degrees longitude. Turn east and walk a quarter circle around the equator. You arrive at 90 degrees east. Path B, here's where it gets interesting. Before walking anywhere, turn east. But wait, you're at the North Pole. Which way is east? Think about it. The North Pole is the northernmost point on Earth. Every direction from the North Pole is south. There is no east. Turning east at the North Pole does absolutely nothing. So you end up just walking south to the equator and then turning east for that quarter circle walk. Same path, right? Same destination? No. Path A ends at 90 degrees east. Path B ends at 0 degrees. You're a quarter of the way around the planet from where you should be. On a curved surface like a sphere, the order of operations matters. South then east is not the same as east then south. Operations don't commute. This failure of commutativity is curvature revealing itself. It's the signature of non-Euclidean geometry. And here's the profound connection. This is exactly what acceleration detects. Velocity is like taking one step. It's a first-order operation. It's local, instantaneous, directional, like pointing north and taking a single pace. Acceleration is like taking 2 steps and comparing directions. It's second order. It requires you to compare north here with north there, and that's when curvature enters the picture. In flat space, your velocity vector can remain parallel to itself effortlessly as you move. North stays north, east stays east. But in curved space, there's no consistent notion of parallel across different points. To compare your velocity at 2 different locations, you have to transport one vector to the other's location, and curved geometry resists this transport. It twists the vector, rotates it, changes it. The technical term is parallel transport, and acceleration measures exactly how much your velocity fails to remain parallel to itself as you move through space. This is written mathematically as nabla subscript v of v, which we pronounce as the covariant derivative of velocity. And this, not dv dt, is the true coordinate-independent definition of acceleration. Now here's where the paper makes a crucial claim that challenges standard physics education. The standard view teaches us that velocity and acceleration are both kinematic quantities, both measuring motion, just at different orders of differentiation. But the paper proves they're fundamentally different in nature. Velocity is blind to curvature, completely, utterly blind. Velocity is a local quantity. It lives entirely at one point in space. It's a tangent vector, an arrow attached to one location in space. Curvature, by contrast, is about comparing different points. It measures how geometry changes from place to place. You cannot see curvature by standing at one point and looking at your velocity vector. Acceleration reveals geometry. It's the minimal kinematic observable that can detect curvature. Because acceleration involves second derivatives, it compares neighborhoods. It asks, how does the velocity here differ from the velocity there? And in answering that question, it exposes the curvature of the underlying space. Think of it like this. If space is a landscape, velocity tells you which direction you're facing, but acceleration tells you whether the ground beneath you is flat or curved. One is directional information, the other is geometric information. Now I want to introduce you to one of the most beautiful ideas in the paper, the idea that acceleration is curvature's boundary shadow. Let me explain what this means through a visual thought experiment. Imagine a sphere rotating at constant angular velocity in three-dimensional space. Beautiful, smooth, uniform circular motion. If you track a point on the sphere's surface, it's moving in a perfect circle. There's no speeding up, no slowing down, no change in the rate of rotation. In the full three-dimensional space, this is geodesic motion, zero acceleration. Now, shine a light on this sphere and watch its shadow on a wall. The shadow of that rotating point doesn't move in a circle. It oscillates back and forth, left, right, left, right. And here's the key. The shadow speeds up and slows down. At the center of its oscillation, it's moving fastest. At the edges, it comes to a complete stop, reverses direction, and accelerates back. If you only saw the shadow, if you lived in the two-dimensional world of the wall, you would think there's a force acting on this point. You would calculate its acceleration using d squared x divided by dt squared and get a non-zero answer. You would conclude that something is pushing and pulling.
But there is no force. The acceleration you see in two dimensions is an illusion. It's a projection artifact. It's the shadow of smooth, force-free motion in three dimensions being projected onto a lower dimensional space. The paper calls this the one-dimensional projection of a two-dimensional geometric obstruction. When you project from a higher dimensional curved space to a lower dimensional flat space, acceleration appears where none existed before. And this isn't just a mathematical curiosity, this is exactly what happens in quantum mechanics. In quantum mechanics, a particle's state lives in an abstract, high-dimensional space called Hilbert space. For even the simplest quantum system, a spin 1/2 particle, the Hilbert space is the surface of a three-dimensional sphere. The full quantum state is a point on this sphere. When the system evolves according to the Schrödinger equation, this point moves along the sphere. And here's what the paper proves. This motion is geodesic. It's force-free. It's the straightest possible path on the curved surface. In the full Hilbert space, the quantum state experiences zero acceleration. But we can't directly observe the quantum state. We can only measure probabilities. When you measure whether a spin is up or down, you're asking, what's the probability of finding it in the up state? That probability is the squared length of the projection of the quantum state onto the up direction. It's written as P equals the absolute value of the inner product of the state with the up state, all squared. And here's where the magic happens. Even though the state is moving smoothly with zero acceleration in Hilbert space, the probability oscillates. For a simple two-level system in a magnetic field, the probability evolves as P of t equals cosine squared of omega t. Not just cosine, cosine squared. Now take the second derivative of this probability. You get d squared p dt squared plus omega squared times p minus 1/2 equals 0. This is the equation of a harmonic oscillator. It shows acceleration, not because there's a force acting on the quantum system, but because we're seeing the shadow of geodesic rotation in high dimensions projected onto our observable, one-dimensional probability axis. And here's something remarkable that the paper proves. The cosine squared form is not arbitrary. It's not just one possible solution. It's the unique solution. The paper presents a rigidity theorem. If probability satisfies certain natural physical constraints, oscillatory behavior, boundedness, and second-order closure, then it must be cosine squared. Not cosine, not exponential decay, not any other function. Cosine squared is forced by the geometry. The paper validates this computationally using data from nitrogen vacancy centers in diamond. These are real quantum systems used in quantum computing research. When you apply a magnetic field and watch the spin state evolve, you see oscillations. And without exception, every single measurement shows the cosine squared pattern. The mean squared error between the observed data and the cosine squared prediction is 10 to the minus 33. That's exact to the limits of computational precision. Now we need to talk about something crucial, something that standard physics education completely misses. There are two fundamentally different types of acceleration, and they produce two fundamentally different types of waves. Type 1, physical acceleration. This is when your world line itself is curved, when you're genuinely deviating from geodesic flow. The covariant derivative of your velocity, nabla VV, is not zero. You're experiencing real geometric acceleration. An electron in a synchrotron is the perfect example. Magnetic fields bend its path into a circle. The electron wants to go straight, geodesic motion, but the magnetic force curves its world line. This is real acceleration. And because the electron is electrically charged, this acceleration couples to the electromagnetic field. Energy leaks away as synchrotron radiation. Light is emitted. The power radiated is proportional to the square of the acceleration. The characteristics of physical acceleration are energy decreases over time, waves are emitted and escape to infinity, the process is irreversible, time's arrow points forward, and you need continuous force input to maintain the motion against radiation losses. Type 2, apparent acceleration. This is when your motion is geodesic, zero physical acceleration, but you're moving through a curved space. And when you project from that curved space onto an observable flat space, acceleration appears in the projection. Quantum oscillations are the perfect example. A quantum spin precessing in a magnetic field is following a geodesic in Hilbert space. The Schrödinger equation describes force-free geodesic flow, zero physical acceleration. But when you project onto probabilities, oscillations appear. The second derivative of probability is non-zero. The characteristics of apparent acceleration are energy is conserved perfectly, no waves are emitted, nothing escapes the system, the process is completely reversible, you can run time backward and return to the initial state exactly, and no force is needed because it's free motion through curved geometry. Both show acceleration in the equations. Both show d squared q dt squared not equal to zero. Both create wave phenomena, but they are opposite in physical character. One is dissipative, the other conservative. One radiates energy, the other circulates it. One requires forces, the other is force-free. And here's the deep insight. The type of wave you get depends on the topology of your space. In unbounded spaces, spaces that extend to infinity, physical acceleration appears as radiation. Energy escapes to infinity. In bounded spaces, compact spaces like spheres or tori, physical acceleration appears as oscillation. Energy cannot escape. It circulates in closed orbits. This is a topological distinction with profound physical consequences. Now let me connect this to Einstein's greatest insight. Einstein taught us that gravity and acceleration are equivalent, the equivalence principle. You cannot distinguish by local experiments between sitting in a rocket accelerating through empty space and sitting on the surface of a planet. But the paper gives us a more precise understanding. Both gravity and pure acceleration are described by the same mathematical quantity. The covariant derivative of your velocity is non-zero, but they represent two different perspectives on what's happening. Pure acceleration means you are curved, space-time is flat. A rocket firing its engines in empty space. Your world line deviates from geodesic flow. You're forcing yourself away from the natural straight-line motion that space-time geometry prescribes. Gravity means space-time is curved and you're trying to go straight. Standing on Earth's surface, the ground beneath you is pushing you away from geodesic flow. Free fall, orbiting, or falling would be geodesic motion, but the ground interrupts that geodesic, accelerating you upward relative to the natural flow. In both cases, you feel weight, you feel force, because in both cases, nabla UU is not zero. The geometric curvature of your world line is the same, only the interpretation differs. In one case, you're curving your path through flat space. In the other, space is curved and you're being prevented from following its natural geodesics. Now let me state the universal principle that unifies everything we've discussed. This is the central thesis of the paper. Acceleration is the observable signature of curvature. Let me unpack this. Velocity, the first derivative, measures motion but is blind to geometry. It's local, it's instantaneous, it cannot see curvature because curvature requires comparing different points in space. Acceleration, the second derivative, reveals geometry. It compares neighborhoods. It detects curvature. It is the minimum observable quantity that carries geometric information. How this curvature manifests depends on topology. In unbounded spaces, spaces that extend to infinity, curvature appears as radiation. Energy escapes to infinity. In bounded spaces, compact spaces like spheres or tori, physical acceleration appears as oscillation. Energy cannot escape. It circulates in closed orbits. This is a topological distinction with profound physical consequences. Now let me connect this to Einstein's greatest insight. Einstein taught us that gravity and acceleration are equivalent, the equivalence principle. You cannot distinguish by local experiments between sitting in a rocket accelerating through empty space and sitting on the surface of a planet. But the paper gives us a more precise understanding. Both gravity and pure acceleration are described